Today's 1.3 lecture worksheets. And you'll see that some of the questions on the worksheets assignment are exactly the same as or similar to the ones that I'm about to go over. Worksheet is when you are given a type of problem that's a problem that involves using a math equation. So you'll find this in math or in chemistry. This is the way to show your work. And so this is not just true about these worksheets, but also when you need to show your work on a quiz or midterm or final. So you're reading the problem and you're underlining any important data, which is those number values, that a number value always has to have a unit. And so the example of this is if you have the number 18, that number doesn't mean very much unless it has a unit afterwards, like 18 years old is a lot different than 18 cents. So the words or the number, the unit right after the number value is so important. And so that's why we look for a number value including the units afterwards, like this one, 5.3 milliliters of water. And then this one, 8.7 milliliters. So what's happening in this problem is you have a graduated cylinder. We've seen that. It's a tall glass or plastic cylinder that is used to measure liquid volumes. And a metal object's dropped into it. And this metal object is dropped into it before the metal object's dropped into it. It initially contains 5.3 milliliters of water. So when you have a number value, 5.3 milliliters, you want to list that as what's called known information. Actually write the word known and then write the number with the unit and then what this number represents. That symbol for this, which is volume, not the word volume, but the letter for volume, which is an uppercase V. And so how do you recognize that that's volume? Because milliliters are the units for volume, liquid volume. So liters or uppercase L is what you're looking for, and that's what you see here. So then when that metal object is dropped in the water, this volume changes to 8.7 milliliters. And that's also because of the unit's volume is another volume or uppercase V. Now, the unknown is part of the question. What's the volume of the object? So the unknown, the thing you're trying to solve for, is also volume, which is also a V. So how to handle this? That we've got three V's. Well, one is the initial volume. That's this one. So this is the initial volume, the 5.3 milliliters. And then the second volume, 8.7 milliliters, is the final volume. And then the third, this is the volume of the object. So there are actually distinguishing three different volumes. So then we want to look for an equation, and all equations in Chem 9 are given. So you will either have it directly on the screen or in a box on a written exam. And this is the best option right here. It is, let's copy this equation. So the equation I found that has three V's in it is delta V, which is the volume of an object. And this delta means the change in. So that's the change in V or the change in volume is equal to the volume of the object, which is V final minus V initial. So I just copied that exact equation. Now you might be thinking, well, I could have just done this in my head. But again, the purpose is to show your work. And so this also becomes important, is make sure that the unknown, the thing you're trying to solve for, is isolated or by itself on one side of the equal sign. You might need to rearrange the equation so that the unknown, this unknown, is by itself on one side of the equal sign. So this already, the object is what we're trying to solve for, already by itself on one side of the equal sign, so we don't need to rearrange this equation. We will need to for another example though. So when this is isolated by itself on one side of the equal sign, then you can plug in the known values with the units so that you can cancel the units. So let's do that. This is the V volume of the object by itself. So the final volume is 8.7 ml. So notice the number with the units minus 5.3 ml. So the units are the thing I look at first, which is milliliters minus milliliters. So this is going to be still milliliters. They don't cancel out. And then this is 8.7 minus 5.3. And I'm looking to write down the entire number from the calculator, which is 3.4. If it were a longer number, like 3.47128, I would write down the whole number. So then you always want to either figure this out with decimal places or sig figs for subtraction and addition. You're looking at decimal places. And so adding that from last time, anytime you've calculated something on the calculator, you want to go back and look at the original number values. If it's subtraction or addition, decimal places. So this is 1 decimal place in this number and 1 decimal place in this number. So our answer needs and already has 1 decimal place. So I don't need to round this. If it were multiplication or division, I'd go back to the original numbers and look at sig figs. So this is set. We want to check that the units are correct and that the answer makes sense. So it shouldn't be too big or too small and should always have units. Okay, so it's a stepwise process to show your work. And let's look at this example. It says calculate the volume. Oh, so the first thing that pops out is the unknown. So the unknown, the thing we're trying to solve for, is the volume. And you don't want the word volume, you want the symbol for volume, V, uppercase V. And they're telling us it's going to be in units of meters cubed. That's M cubed or cubic meters, different ways to say this. Okay. And so this unknown has some parameters, which are the known information about it. The width is 25 meters. So we can write that the width is 25 meters. And this is going to be more useful as the symbol for width, which is W. Okay, because then we can find an equation that has everything. The length is 45 meters. So the length 45 with the units M. More useful as the symbol for length, which is an L, lowercase l. And then the height, which is 0.65 meters. And the symbol for height is more useful, that's H. And that's because we're trying to find and look for an equation that has the unknown and all the known symbols. So we're looking for an equation that has this, 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 and this. This looks like the volume of the cube is LWH. So what we're trying to solve for, this volume is already by itself on one side, the equal sign. So that means I can go ahead and use this equation, plugging in each number with the units, 45m times 25m times 0.65m. And so before I go to the calculator, before I look at the numbers, I'm going to deal with the units, which is m times m, or meters cubed. Now I'm going to put this into the calculator, which is 45 times 25 times 0.65. Now, it didn't actually matter what order this was listed. The 45 was first, but the 25 could have been first, or the 0.65, because multiplication, it's all the same when you put it in the calculator. It doesn't matter the order. And so I write down the entire number from the calculator, 731.25. And now I'm looking at the original number values, which are 25m, that has 2 sig figs. 45m has 2 sig figs. And this is a leading 0 with a decimal and a 6 and a 5. So that also has 2 sig figs. So our answer needs 2 sig figs. So I'm going to round this to 2 sig figs, which is going to be the 7 and the 3. And I don't want to cut this off and say meters cubed. So don't think about doing that. Because if you had $731, what this is really closer to is $730. And that's why I'm going to write 730 meters cubed. And I use dollars because if you had $731 that suddenly became $73, you'd be pretty upset. So this is rounded. This has two sig figs, the 7 and the 3. And remember, this 0 is not significant because it's a trailing 0 with no decimal. Okay, so when you have a 0 on the right, it's only significant if there's a decimal. So that's our answer there with the two sig figs. And this should solve that. Now, number 2 is a solid object has a mass of 35 grams. So this is a number with units. So that's known information. And this is, let me write it like this. The mass is 35 grams. And we don't want the word mass, but we want the symbol for mass, which is a lowercase m. Now, lowercase m is used a lot. The lowercase m we already saw here is meters. This is a lowercase m that's representing mass. And we've also seen a lowercase m that's the metric prefix milli. Well, I didn't invent it. I don't like it, but that's what we got to live with. So this lowercase m represents mass when it is a variable. There's density, which is 2.70 grams per centimeter cubed. And this is uppercase D. And the unknown, what we're trying to solve for, is volume. And the word volume not as useful as the symbol for volume, which is uppercase V. So finding an equation that has the M, the D, and the V is looking like this one. This is density equals mass over volume. Now, what we're trying to solve for this time is the volume. And volume is down here. It's in the denominator. And it's not isolated. So the first thing I want to do is isolate the unknown, the thing I'm trying to solve for, which is volume. So I'm going to multiply this volume times the density. Density times volume equals the mass. And then divide so that volume is by itself on one side, the equal sign. So then I can solve for volume, which is V equals the mass over the density, and plug in those numbers. So that's 35G over 2.70 G over centimeter cubed. The units that cancel out is this G in the numerator and this G in the denominator. Meanwhile, this centimeters cubed is in the bottom of this bottom fraction. So what happens to this is it moves up. It's no longer down there and becomes a unit that is the numerator, which is important because I'm going to write an equal sign, leave a bunch of white space, and then write centimeters cubed over to the right. So this is good because centimeters cubed are the units for solid volume. Now we'll see this in lab. We actually have a cube that we're going to measure and be looking at densities. But this is when you have the volume, which is the space something takes up. The volume of a solid can be calculated or it can be measured. And this is something that is units, centimeters cubed, could also be meters cubed. It's always going to have that M. So then we take 35 divided by 2.70, and I've got this long number, which is 12.96296. And now I've got to take this long number and round it by looking at the original numbers, which is 35 grams that has 2 sig figs and 2.70 that has 3 sig figs. Use the lower value, which is 2 sig figs. And so this is going to be the 1 and the 2 is what I'm keeping. The next digit is a 9, so I'm going to round up to 13, and this is centimeters cubed. Basically looking at all the matter in the universe and trying to categorize and organize it. Because when you got a whole bunch of stuff, which is all the stuff in the universe, it's made out of atoms, somebody decided to try to organize it. And so when you've got matter, it's broken down into two main buckets, substances and mixtures. And basically, substances are small scale and even down to submicroscopic, and mixtures are large scale, what you can actually see. So I've been using this term macroscopic versus microscopic, and even molecular views. Okay, so mixtures are things generally that you can see. And substances tend to be smaller, like elements in the periodic table, and compounds, which are when you put elements together in a chemical reaction, you'll form a compound. So I'd like to point out the periodic table, which there's a lot of different versions of the periodic table, but this one is at the back of the worksheets page that has the worksheets pack. This one at the back has the element symbols with all the names also. So this periodic table in the front is, oh, I gave my periodic table away. That was on page 2. Periodic table in the front doesn't have the element names. So this is thinking about an element like the element hydrogen. That would be always diatomic, H2. Or when you put hydrogen together with oxygen, H2O, that's a compound. So that's more than one element is a compound. But you can have an individual element like Fe, so that's iron, and iron is also classified as an element. This is an example of an element that exists just as individual atoms, compared to H2, which is an element that exists always as a molecule, two atoms of hydrogen bonded together. So a compound is when you have two different elements from the periodic table. Homogeneous and heterogeneous mixtures. These again are part of mixtures. Generally, you can see the parts of a heterogeneous mixture. Something like a pepperoni pizza. You can see all the different things that are in there and you know that they're different. Compared to a homogeneous mixture, where you know that there's different parts in it, but you just can't see the different parts, like air. The air in this room has oxygen, carbon dioxide, nitrogen, lots of other gases, but we can't see all those different parts, making it homogeneous. Okay, so in these examples, we want to classify if it's a substance or mixture, and then broken down if it is a substance, if it's an element on the periodic table, or a compound that is elements bonded together. And if it's a mixture, is it either homogeneous or heterogeneous? So the bar of deodorant soap. I think in the lecture videos, I showed you a picture of the bar of deodorant soap. And that bar of deodorant soap is something that has green strips in it and white strips in it. We know there's different green and white parts in it. We can see those, so that makes this a heterogeneous mixture. And then the copper wiring. So copper is an element name, and the element symbol is Cu. So anytime you have an element on the periodic table, that is a substance. And it's just an element alone, it's not bonded to anything else. Helium gas. So again, helium is the name of an element from the periodic table. This is He is the element symbol. And so that is another element that's a substance. When you have a sample of laughing gas, so laughing gas is the chemical formula N2O. And so N2O is two elements. So you've got nitrogen bonded to oxygen. Two different elements is a compound. Don't call that a mixture, though. A mixture is when you have two different things, completely different things that are not bonded together. But when you have two different elements, two different atoms that are bonded together, that's a compound. All right, when you have a cup of mayonnaise, so mayonnaise is this white kind of viscous look to it. It's a semi-solid, I guess. That cup of mayonnaise is a whole bunch of different ingredients, and you can't see the different components. So this is a homogeneous mixture. Water. So water is the chemical formula H2O. We talked about water in lab last week. And so this shows that there's the element hydrogen and also the element oxygen. So that's definitely going to be a compound, which is a substance. Now, when you take sugar and you dissolve it in that water, now you've got two things. That makes that a mixture. And then let's think about, is it a heterogeneous mixture where you can see the parts? Can you see the sugar separated from the water? Or is it a homogeneous mixture like a solution where the sugar has dissolved in the water, making it a homogeneous mixture? And you can't see the sugar once it's dissolved in the water. Now, same thinking about water. When you take water and you boil it and you have steam coming off of that pan of boiling water, you still have water. It's still H2O, but now it's the gas form, okay? And so it is still that original compound. It hasn't broken down. It's still the hydrogen and the oxygen, but now it's as a gas instead of a liquid. And then air, we talked about being a mixture of many different types of gases. We'll talk about air in a lab, future lab, as well as air and air pollutants in this module. Okay, so kind of fun. You don't have to learn the element names. You can always use this periodic table, which has the element names with the symbols. But if you decide you want to, okay, that does no good. If you decide you want to learn the element names and do some good in the world, this is called free rice, where you can just test yourself. This element name platinum is the element symbol PT, and I just donated 10 grains of rice somewhere. So this is gold, this is the element symbol AU, and I got up to 20 grains. So anytime you're bored and just thinking like, oh, I can do something good for the world, you can do something good for the world. Just wanted to show you that. And so this link looks like so we've got, this is focusing in on those elements and compounds is what we can't see. So this is models of atoms, molecules, and compounds. So elements are anytime you have one of these elements from the periodic table, an element symbol is going to be one type of atom. And the majority of the 118 elements on the periodic table, most of them exist in the universe as individual atoms. So this is individual little spheres. And these individual atoms are called an atomic element. And like I said, most of the elements on the periodic table, if you're out in the universe, you'll find iron as individual atoms. It's a chunk of iron, but when you break it down to the smallest part, this is what you're going to get, little individual atoms. Same as gold, or let's take anything on here, chromium, dy, any of the elements on here, 118 of them, most of them are individual atoms. Now, a few of the elements on the periodic table, just a handful of them, exist naturally as diatomic, or two atoms bonded together. And this is two atoms that are the exact same element. So notice that these individual atoms, the atomic element, are the color purple. So these two atoms that are bonded together are both white. And so this is typically hydrogen is used for the white color atoms. They're not actually white, but it's used in molecular views to always symbolize hydrogen. So this is hydrogen, which is H2. It's always two atoms bonded, and those two atoms are the same color. So this is called a molecule. when you have two atoms bonded and the bond is such that those individual atoms no longer have their boundaries, they're no longer individual spheres. So these atoms are smushed together is what I call the view. And it's called a covalent bond. And this is something we'll look at the chemistry of, but when it's smushed together, they are no longer individual spheres, and this is called a molecule. And there are on the periodic table 118 elements, but just these H2, N2, O2, F2, Cl2, Br2, and I2 are always going to be present as diatomic, which means that you're never going to have hydrogen alone. It's always going to be H2. Now you can have hydrogen alone bonded to another atom, like is H2O, but it's never just going to be hydrogen by itself as one atom, okay? So it's never going to be an atomic individual atom. And that's because these atoms are very reactive and they'll always react with another atom of itself. So when thinking about elements, an element, whether it's atomic or molecular, is going to be one color. And that's to distinguish from a compound, which is when you have different elements bonded together, which would be shown as different colors. So here is a compound because you've got the atoms that are purple and the atoms that are red. So that's a compound. It's also a molecule at the same time, because remember the definition of a molecule is when you have atoms that are smushed together and they no longer have their individual boundaries anymore because of the bond where the atoms are sharing electrons. It's called a covalent bond. We'll talk more about covalent bonds later. So this is another example of a molecule where you've got this atom that is black. It's usually carbon. And then you've got 1, 2, 3 hydrogens or 3 white atoms. Okay. And so this is, again, a compound because they're different elements, different colors, and also because these atoms no longer have their individual boundaries. There's a little bit lost on that side when it's bonded. These are also molecules. Okay. So when you have a mixture, now a mixture is when you have different things, can be different colors. Here you have one type of atom or one type of element that's red, element number 1, and this is another type of element that's purple. You have 2 different types of elements. They're both atomic elements, but they're not bonded together. And so if you have 2 different things not bonded together, this is the example of a mixture. Here we've got 3 different things. We've got this element, we've got this different element, and then we also have this compound or molecule. And so all these things are not bonded together. And so this is an example, again, of a mixture. So when you have different things thrown together that are not all bonded together, that's a mixture. Okay, so let's look at these examples here. When you have, this is definitely 2 different colors. You've got your black atoms and your white atoms. This is a compound because those atoms are bonded together. Okay, so we're just classifying element, compound, or mixture. This, you could also say that these are molecules as well when they're smushed together. So when you've got this 2 atoms bonded together, the same color, this is called a molecular element. So first of all, it's an element that is one type of element, one color, and these are molecules when they're smushed together. Okay, so a compound is when you have 2 different colors. Element is when you have one color. Here I've got this molecular element. And I also have this which is an atomic element. Both of these are present and not bonded together, making this a mixture. Okay. We don't distinguish between heterogeneous or homogeneous mixture at this level because heterogeneous or homogeneous mixture is something you can see at the macroscopic, which is with your eyes, versus a molecular view is not something that can be distinguished like that. All right, so let's take a look at this, which is the next box. This is a compound when you have two different elements, two different colors. This is a molecular element. It's one element because one color, but it's a molecule. And because all of those are not bonded together, this is also a mixture. This box down here, we have individual atoms. So this is one type of element because they're all the same color. And this is individual atoms, which makes it an atomic element. All right, we have the same atomic element here, individual atoms. And there's also, this is a compound when you have two colors or two different atoms bonded together. And then this is a different compound. This is two different atoms bonded together, two colors, making this another mixture. Okay. More about element symbols. And like I said, you have your notes. You have the periodic table with the element symbols and also the element names. You definitely don't need to memorize any of that. But should you want to, this is the ones that we use. There's about 40 of them, about 40 of the elements in the periodic table that we most commonly use in Chem 9. And they're listed by group number, which is a way to organize the periodic table. That is by how these elements in a single column or a single vertical column, they are related because they have similar chemical and physical properties. Like everything in this first column on the left, they're all very reactive metals. So it's a chemical family. They're very similar and they react the same. They kind of look the same, but like a family that's a human family that's similar, but they're not all exactly the same. So these elements are similar in how they will react, but not completely the same. Okay, so the idea here is basically just recognizing what the atomic number is on the periodic table. So that's the whole number value that's associated with each element. It's kind of like each element's address. Each element has a location, and that's a box, and that box has a number. Just like you have an address where you live and it has a number. So the whole number that is always assigned and the same as that element's symbol. So sodium, for example, is Na, and that is the whole number value 11. We'll see later that this whole number, this atomic number, represents the number of protons that's present in the element. Okay, the family number is the number at the top. And so that is basically, like I said, this vertical column, all the elements have the similar chemical properties or the similar chemical properties. That's why they're all listed together. The family number is a way to basically say, okay, they're all the same, so let's call them this family number or even a family name. And so family number 1A actually has the family name called alkali metals. Let me write that properly. So this is alkali metals is the name of family number 1A. And it's given the name because they all have this property that they're very reactive metals. Strontium is Sr. And Sr has the atomic number 38, and this can be found in family 2A. And these are called the alkaline earth metals. So one question I could ask is calcium an alkaline earth metal? So calcium has the element symbol Ca, and it's in family 2A, it's in this column. And so yes, it is an alkaline earth metal. It's a way to name an element by its family. Okay, silicon is the element symbol Si. I should also add that the first letter is always uppercase and the second letter is always not uppercase or lowercase. So you're never going to have two uppercase letters. And notice that about all these element symbols. If you have only one letter, it's only one uppercase letter. Okay. So silicon is atomic number 14, and this is in family 4A, which does not have a name. Now, silver is based on its old Latin. A lot of these are based on their Latin or Roman or Greek, or even predating all those times. This silver was discovered before the convention of using the first letter and of the name. So this is Ag, argentum is the Latin name. And so this has the atomic number 47, and it's in family 1B. And so this B is the B series, which are called the transition metals. And they are the 10 columns in the middle of the periodic table. I probably should also point out my many periodic tables, because I love the periodic table. I've got like 20 in the house in all different versions. I've got socks, I've got t-shirts, I've got mugs, I've got artwork. It's a very organized periodic table, and one reason why I love it is because it's organization at its best. Okay, so sulfur is S, and this is the atomic number 16, and it is in family 6A. Copper didn't get CO, that's cobalt, the next one. Copper is Cu from its Latin name cuprum, and this is the atomic number 29, and it's in family 1B. Cobalt is atomic number 27, and this is in family 8B. Chlorine is not CH, but it's Cl. It's atomic number 17, and it's in family 7A, which are called the halogens. And halogens, this vertical column over to the right, are very reactive nonmetals. Carbon is family C, is element symbol C, and it is atomic number 6 and family 4A. I'm putting in this, this is the periodic table you'll see a lot embedded in quiz questions, let's say, or practice quiz questions. And it is just the element symbols without the names. And so it has the family numbers, and just a quick overview of this is the family numbers 1A, 2A, and 3A. Notice I jump over from counting 1, 2, and then over to the right to 3A, because this center section, those are those B series or transition metals, okay? And the A series are these 2 columns on the left and then 6 columns on the right. And the A series are called the representative elements. And these elements in those columns, representative elements in those columns, do exactly as I was saying, is that these elements listed in one column all have similar chemical and physical properties. This is also true about elements in the B series columns, but they're not as good. They're not as representative. They don't do all this perfect thing like family 1A are all very reactive metals. So here we've got the names listed with the element symbols. These are the most common ones. So this is a great page to bookmark. And then also, you know a lot about the periodic table just from what we've gone over. So because I told you why I love the periodic table, it's organized. And one way it's organized is by these columns. And so we know that we could add the columns or family numbers to these columns. So this is 1A, and I can add 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And then some of these also have names. So remember, 1A is your alkali metals. Those are very reactive metals, everything in this column. 2A are your alkaline earth metals. And so all of those elements in this column are reactive metals. This is 7A. I want to write 78, but 7A, jumping over here. These are your halogens, and halogens are very reactive gases. And 8A are called noble gases, and those are non-reactive gases. They don't react or they're inert. They're called noble because they basically rise above everything that's going on in the periodic table where all these elements are reacting with each other. There's also something to point out, which is a stair-step line that I'm going to add to here. And so everything to the left of this stair-step line are metals. So everything to the left and below the stair-step line are metals, and then everything to the right and above the stair-step line are non-metals. Okay, and so this center section, or the B series, these 8 columns here, are called transition metals. So the way this periodic table is organized, you already know a lot about it just by how these boxes are. So it's not a perfect rectangle with boxes. It's arranged this way with these spaces and gaps on purpose so that all of the boxes in a vertical column are a family. And a family is elements that have similar chemical and physical properties. So we know that alkali metal would be A, and an alkaline earth metal would be F. A halogen would be this E, and the noble gas would be B. Transition metal would be anything in that B series, so that's C. A non-reactive gas would be a noble gas, and so that's B. And a very reactive metal, that's an alkali metal. That's in family 1A all the way over to the left, or A. A very reactive nonmetal is the definition of a halogen. So that's family 7A or E. And then a semiconductor, I didn't get to talk about yet, but a semiconductor is halfway between being a metal and a nonmetal. And so basically being on this line. And so that would be D here. And so if you go back and look at D on the periodic table, that box is this Si, which is silicon. And silicon is called a semi-metal, or also called, let me get you back here, a semiconductor. And silicon is super important in all of our lives because it can conduct electricity in a controlled manner, and it's used in processing information or a computer processing chip, a CPU. And so this is in your smartphone, in your desktop, in your laptop. You all have a life based on the semiconductor silicon, whether you like it or not, because it has the ability to conduct electricity in a controlled manner. Hydrogen. So hydrogen can act like a metal when it's a box in family 1A, which it is. But I also added this box here, where hydrogen can be a box right above fluorine and act like a nonmetal and be placed in family 7A. So hydrogen is a very rare atom where it can be in 2 places on the periodic table. It can act like a metal, and it can also act like a nonmetal. And we'll get to more of that in talking about bonding, but hydrogen can act like both a metal or a nonmetal, but mostly what we know hydrogen as is the gas that is H2. So mostly hydrogen is present as H2. It's a molecular element. It is bonded to itself as a diatomic molecule. And hydrogen can be present as individual atoms, and that's already bonded to other atoms when it's in a compound.